Hello, my name is Isra Jahan. In this project, I analyzed a healthcare dataset to predict patient test results using machine learning models, especially Random Forest, XGBoost. I will walk through the dataset, processing steps, model building, tuning, and finally compare the results and discuss real-world impact. In the dataset overview and EDS section, I will cover all the dataset and describe all of column and data types. This is a preview of the dataset showing the first 5 records. Each row represents a patient and the columns contain demographic, medical, and hospital-related information. The dataset contains 55,500 columns and 50 rows. It means we have a 55,500 patients record and 15 features. Also included the data type and information. The dataset includes features such as name, age, gender, blood type, medical condition, billing amount, and the target variable test result. I check for missing values to ensure the data quality. That helps determine whether the cleaning is needed before the modeling. This shows summary statistics like mean, minimum, and maximum values. For example, the average and billing amount help us understand the general distribution of the data. The target variable is test results, which has 3 classes: normal, abnormal, and inconclusive. This histogram shows how patient ages are distributed. It helps identify common age groups and detect any unusual patterns. To prepare the data for machine learning, I performed several pre-processing steps. I converted categorical variable into numeric format using one-hot encoding. I created a new feature called length of stay by calculating the difference between discharge and admission dates. This feature captures how long patients stay in the hospital and can be an important indicator of their medical condition. Also, I scaled numeric feature to ensure they are on a same scale, which helps improve model performance. In this section, I will describe about random forest model. I built a random forest model with 100 trees and control its complexity using depth and leaf node limits. I used a square root feature selection to improve generalization. The model was trained on training data and evaluated on test data using accuracy, precision, and recall and F1 score. I also measured training time to assess efficiency. The baseline random forest model achieved an accuracy of around 0.33. However, the F1 score is much lower at 0.26, which indicated that the model is not performing well across all classes, especially in handling class imbalance. This suggested that the baseline model is not sufficient and required tuning to improve performance. After hyperparameter tuning, the best configuration included 100 trees with no restriction on depth and a minimum split of 2 samples. Allowing the trees to grow fully increased model complexity, which helped capture more pattern in the data. However, this is also significantly increased the training time to about 199 seconds. This shows a trade-off between performance and computational cost. After tuning, the random forest model showed a significant improvement. Accuracy and F1 score increased to around 0.43. The biggest improvement was in the F1 score, which indicated that the model is now performing more consistently across the classes. This confirmed that hyperparameter tuning had a strong positive impact. I analyzed feature importance to understand which variables had the greatest impact on the model prediction. Feature importance shows how much each feature contributed to the decision-making process of the random forest model. In this plot, the top 10 most features are displayed. Features with a higher importance value have a stronger influence on predicting the test results. In this plot, we can see that the billing amount and the room number is the higher. After hyperparameter tuning, I evaluated the random forest model using multiple performance metrics. The tuned model achieved an accuracy and F1 scores around 0.43, showing a significant improvement overall the baseline model. The increased F1 score indicates that the model is now performing more consistently across all classes, improving its ability to handle class imbalance. I also evaluated the model using ROC-AUC with the one versus rest approach. The ROC-AUC score was approximately 0.50, which suggested that the model limited ability to distinguish between the different classes. Although the tuning improved accuracy and F1 scores, the ROC result indicate the dataset may not have a stronger predictive features. XGBoost is a powerful boosting algorithm that builds models sequentially and improves performance by correcting previous errors. This step-by-step learning process makes XGBoost very effective for structured data and predictive tasks. In this session, we will train our data with the XGBoost model. This is the baseline XGBoost model performance before tuning. I evaluated the baseline XGBoost model using accuracy and F1 macro. The model achieved an accuracy of approximately 0.375 and F1 macro score of 0.374. These results indicated that the model performs moderately, with similar values for both accuracy and F1 score, suggesting a balanced performance across classes. However, the overall performance is still relatively low, which indicated that the model may not be captured a strong pattern in the dataset. This suggested that the further improvement through hyperparameter tuning is necessary. After performing hyperparameter tuning, the best configuration for the XGBoost model includes a learning rate of 0.2, 200 estimator, and maximum depth 7. The learning rate controls how quickly the model learns. A value of 0.2 allows the model to learn faster while still maintaining stability. The number of estimators set of 200 means the model builds 200 trees sequentially, allowing it to improve the predictor step by step. The maximum depth of 7 controls the complexity of each tree, enabling the modeling to capture more detailed patterns in the data. I also use subsample value 0.8, which means the model uses 80% of the data for each tree, helping reducing the overfitting. Finally, I call sample by tree was set of 1, meaning all features are used when building each tree. I used early stopping to preventing overfitting by stopping training when performance stopped improving. With a learning rate of 0.2 and max depth of 7, the model balanced learning speed and complexity. After tuning, the XGBoost model improved slightly, achieving the accuracy and F1 macro of around 0.383. This indicated consistent but limited performance improvement. I evaluated the model using ROC-AUC with a 1 versus rest approach, and the score was approximately 0.48. A ROC-AUC score close to 0.5 indicated that the model has very limited ability to distinguish between classes, performing only slightly better than the random guessing. This suggested that even after tuning, the model is not effectively separating the different test result categories. This limitation may be due to a weak predictive feature or noise in the dataset. After tuning, the XGBoost model achieved an accuracy of about 0.383 and the F1 macro score of 0.383. The ROC-AUC score was around 0.48, indicating limited ability to distinguish between classes. In the reflection section, I will discuss which model is performed well. In this project, I compared a Random Forest and XGBoost model for predicting patients' test result. The tuned Random Forest performed better, achieving higher accuracy and F1 score compared to XGBoost. Although the XGBoost is a powerful boosting algorithm, its performance was limited in this case, likely due to the dataset characteristic. In a real-world healthcare, predictive models like these can provide a significant value. By predicting test results, hospital can identify high-risk patients early and prioritize them for immediate care. These enable faster diagnosis and timely treatment, which can improve patients' outcome and reduce complications. Additionally, this prediction can help hospitals allocate resources more efficiently, such as managing hospital beds, assigning doctor, and scheduling tests. Overall, using machine learning in healthcare support more proactive, data-driven decision-making and improve both efficiency and quality of care. From this project, I learned that hyperparameter tuning can greatly improve model performance, especially for random forest. However, model success depends on data quality and feature engineering that the choice of algorithm. I also observed that no single model is always best, and there is often a trade-off between performance and computational cost. Finally, the low ROC-AUC values highlighted that the importance of having strong predictive features. Thank you.